So our last set of slides is going to be looking at the activity of plate tectonics and the features that are produced by the movement of the tectonic plates. It'll probably take 2 slide sets to do this. I never know when I start on the first set, like if it's going to be 2. But I assume it is because there are a lot of slides and there's a lot going on at the boundaries. Worst case scenario, it goes to 3, but probably just 2. This little slide here, you can take a look at it. It is a comic strip that I like quite a bit, but the point it makes, I think in an amusing way, is that the plates don't move very fast. So if you wanted to play a video game of plate tectonics in real time, it would be very, very slow. So let's talk about the plate boundaries and what happens there, what kind of features we see. There are 3 types of plate boundaries, or 3 general categories. We'll see there's some more details once we get into them. The divergent, where the plates are pulling apart. The convergent, where they push into each other. And the transform, where they slide past each other. And these actually correspond with some of the lab exercises that you did. Problem 1 was a divergent boundary, problem 2 was a convergent boundary, and number 6 was transform. So what do we see going on there? Well, a divergent boundary, we're going to look at rifting and seafloor spreading. A convergent boundary, there are actually a couple different flavors. We will talk subduction zones and continental collisions. And then the transform boundaries have kind of more limited features, but we see them associated with mid-ocean ridges, and we also see them sometimes on land. So we'll take a look at all of those as we go through these slides. We're going to start with divergence because remember we started kind of in the evidence area with seafloor spreading and the idea that the continents had all been together. So let's take a look at what happens when plates pull apart. If we were doing this in the classroom, what I would do is I would just ask the class, what is likely to happen if 2 plates pull apart or if a continent fractures and pulls open? And so what you think would happen if you kind of think through the problem is really what does happen. So let's start with this picture in the upper right-hand corner. You can see that things kind of dome up a little bit because of the heat, but really it's that second drawing that I want to take a look at in this bottom drawing. As we pull a plate open, one of the things that happens is we get what's called a rift valley. So we don't get a crack that opens all the way down into the mantle. What actually happens is faults form. They are normal type faults where the hanging wall slides down and away, and they actually kind of fill in the gap. And you can see the result in these 2 drawings is that the crust is getting thinner as the pieces kind of slide down to fill in that gap. So we get this feature called a rift valley with normal faults on either side. And as you might expect, water would collect there because it's a low spot on the landscape, and so you can see they've got some lakes drawn in. The other thing that happens is that because the crust is thinner, there is less pressure on the mantle underneath. Now normally that mantle would be solid, but it is under conditions of very high temperature. It is the high pressure that prevents that material from melting. So when we thin the crust, the pressure is reduced and the underlying mantle melts. Now once we have molten rock, that molten rock is less dense than the surrounding solid rock, and so it begins to rise up to the surface. It intrudes into the fractures that we've made in the crust and makes its way to the surface and gives us volcanoes. Now, because we have done kind of a large-scale melting of the upper mantle, the composition of the mantle is ultramafic, And by the time this molten rock makes its way to the surface, the composition has changed a little bit and it is mafic material. Mafic volcanoes, if you remember back to our discussion of volcanoes a few weeks ago, mafic volcanoes tend to be dominated by lava flow activity and tend to be shield volcanoes. So where can we see this? If this is actually what would happen, we ought to be able to look around the surface of the Earth. And one place where we can see this happening is in East Africa. And so this is what we call the East African Rift. The East African Rift starts down here at the bottom, this long, narrow lake. It actually splits into two branches. The rift that has a lot of lakes in it, the kind of the low spot, is labeled with these two rifts, and then there's also a branch of the rift on the right-hand side. You can see there's a lake up here at the top of the photo, and that's approximately where these two branches join back together and head off the screen to the north. If we focus in on the area inside this yellow box to see what does this rift look like up close, first of all, you notice the long, narrow lakes. And if we were doing this in Google Earth, we could actually kind of see the shape of the valley a little bit better. We're going to zoom in on the area inside that yellow box, and we find a shield volcano. And you can see that very low viscosity lava that we associate with mafic igneous activity is giving us these extensive lava flows coming off of the volcano. So the next question might be, well, what happens if we keep pulling this apart? So if we take more time, this is kind of the early stages of rifting. If we continue to pull it apart, what's going to happen is that at some point we won't be able to fill in that gap by faulting the continental type crust. So if you look at the top figure here on the slide, you'll notice that right there in the middle, instead of having light colored kind of thick material, you have very thin dark material. And what that's meant to represent is that the gap is now being filled in only with mafic igneous rock. So this igneous activity that's occurring here is providing the material that will fill in that gap. And as the gap continues to widen, we will open it up into an ocean basin. So the stage after the Rift Valley is to have kind of a long, narrow seaway. And in the center of that seaway is our fracture, and it's kind of filling in with this mafic igneous rock. You'll notice the crust never gets very thick, because as we make new crust here, we pull it apart. And so we keep adding a little pulling apart, adding a little pulling apart. So that ocean type crust is what forms here, and it never gets very thick. If you remember back to last week when we talked about the different types of crust, we said oceanic crust is mafic, it's thin, it's only a few miles thick, and now we can see why, because it's forming where two plates pull apart. So let's take a look at a location where we can actually see this happening. This is north of the pictures that we looked at previously. You can see I've got the rift labeled here, the East African Rift. And when it gets up to the Red Sea and the Gulf of Aden, it has actually opened up the gap enough that we have this narrow seaway. And in this particular location, things are pulling apart kind of in three different directions. If this continues to pull apart, then what we will see happening is the formation of an ocean basin. And so if we were to go to the middle of the Atlantic Ocean, for example, we find the mid-ocean ridge. This is kind of a mature divergent margin. We have seafloor spreading. You remember that's one of our pieces of evidence for plate tectonics when we finally figured out what was happening at the mid-ocean ridge. The elevated temperature of the igneous activity makes the crust there float a little higher on the mantle, and so that's why we have the mid-ocean ridge. You will notice on this drawing at the middle of the mid-ocean ridge, we actually still have a rift. There is normal faulting and there's a little valley at the top of the ridge, and that's where our igneous activity is occurring. The other kind of interesting feature that we find here is that because the volcano is erupting underwater, it's producing a unique kind of lava that we call a pillow lava, because the lava kind of bubbles up and seals off very quickly. The structure of the ocean crust you can see in this diagram. You'll notice that at the top we have the pillow lavas. Underneath that we have a series of vertical fractures that were the feeder dikes, the feeder intrusions for the pillow lavas, and under that are the more massive intrusions that were feeding those vertical wall-like dikes. And then underneath that we have this kind of greenish colored rock, which is mantle type material. So this sequence together is actually what we find when we drill into the ocean floor. The pillow lavas on top, the feeder dikes, the big intrusions, and then if we were to drill far enough, we would find the green mantle rocks. If you notice off on the left-hand side of this diagram or on the right-hand side, you'll notice they've got kind of a lighter colored shading, which represents the sediment that then slowly covers that up, and so that ends up being the top layer of ocean crust. What's really interesting about this is that while we haven't had the opportunity to drill all the way through the ocean crust, there are places where this set of layers has been caught up in a collision between plates and pushed up onto land, and we can see the whole set of materials. So that's the overview of divergent margins. There is a summary slide here that has the things that we just spoke about. So the rift valley that we find on land with the normal faulting and the mafic igneous activity kind of filling in the cracks. And then as it widens, we go from a narrow seaway to a full-fledged ocean basin. One of the interesting things I would point out is if you look at the edge of an ocean basin, we have what's called the continental shelf. And if you were to look very closely at that, what you would find are the normal faulting and the edges of the original rift valley preserved. Usually by the time we get to this ocean basin kind of mature stage, that material is covered by a very, very thick layer of sediment. And that makes what we call the continental shelf. So the teaser for the next set of slides will be the convergent margins. We will talk about what happens to that ocean crust that we created. And remember, that original ocean crust is very similar in composition to the mantle. And also remember that while we focus on crust, we really should be talking about lithosphere, because the crust is the part we see on top, and it's relatively thin compared to the mantle material that is permanently attached that makes up the remainder of the lithosphere. So that will be the next slideshow. We'll talk about what happens to that ocean crust and really ocean lithosphere.